I am delighted to introduce Deepti Gandluri, who is a manager at Google. Is that a fair way to introduce you?
I don't introduce myself that way yet, but sure.
Deepti is a very important WebAssembly person at Google, and she is going to talk to us about her work on WebAssembly at Google. Take it away, Deepti.
Thank you. Hello, everyone. I'm Deepti. I'm a software engineer at Google, and I lead a lot of the WebAssembly standardization efforts on the Chrome team. WebAssembly is close to my heart. I've been a part of the community for a very long time, so it's a pleasure being here. So in this talk, a lot of what I am hoping to do is talk about WebAssembly and the web, set some context around how WebAssembly fits into the broader web ecosystem, talk about why performance matters to us, and then lead into some performance extensions and memory utilization extensions, and talk about open questions. For a lot of this talk, I'm hoping to not cover the problems we've already solved, but talk about some of the future-facing and open questions that we have going forward or see into the future. So to understand a little bit more about how WASM fits into the web ecosystem, I want to talk a little bit about the history of WASM. This is an incomplete history, so let's start with native client way back in 2008. I've abstracted this time chart to just significant events. I'm sure there's stuff here that I'm missing. So way back in 2008, Native Client was announced. Native Client is a sandbox for running C and C++ code in the browser efficiently and securely. When we jump forward a few years, Portable Native Client Pinnacle was announced, and the Pinnacle extends Native Client with architecture independence. So somewhere around the same time, Emscripten started as a research project. Emscripten, for those who don't know, is an LLVM or Clang-based compiler that compiles C and C++ source code to WASM now, but back then the primary target was JS. And then ASM.js as well, primarily for execution in the browser. So around this time, kind of the 2013 timeframe, we saw a lot of games and applications being ported to native client or compiled to JS using Emscripten. But both of them had their own disadvantages. So Pinnacle worked only on Chrome, so it really wasn't very portable. And with the Emscripten and ASM.js pipeline, you had to do some very careful optimizations, very careful things to make them performant, and so that you don't fall off performance cliffs. So from 2013 to 2015, a lot of the tooling teams in these companies got together and started working collaboratively, and WASM was announced in 2015 and then released in most major browsers in 2017. And now we're a long ways away from 2017, and a lot of things have happened since then. We've extended WASM with threads and atomics, fixed with SMD, exception handling, garbage collection, memory 64, hopefully JSPI coming soon. This kind of the 2025 plus portion is what I'm hoping to talk about today. So I am representing Chromium here. So I want to talk about the guiding principles of Chromium in terms of abstracting it a little bit away from the runtime itself. So there are four guiding principles. Speed, because the speed of rich web applications is really important to us, and one way we kind of service that is developing our own JavaScript engine called W8, which is what I work on. The speed of page display is also quite important to us, and which is why we have our own rendering engine, Blink. We also pay attention to the speed of user interactions from starting the browser to common tasks like clicking a button and kind of just minimizing the lag everywhere. So the other thing here is security. We want to provide the most secure environment for users. So security should be usable. So if you have evil.com, you don't want a permission that says, do you want to go to evil.com? What you want to be able to do is have consistent permissions that actually default to doing the right thing by the user. Stability is also quite important. Browsers are now a lot more than just content viewers. They're a platform in of themselves. They're ubiquitous. Everyone uses them. So we do have a responsibility to make sure that they're stable and backwards compatible. The fourth thing is simplicity. Simplicity can mean a lot of different things. In the context of UI, it can mean just a simplistic interface for people to interact with. But even when the technology is sophisticated, we want to have a very simple abstraction that we present to the user. So in the context of WASM too, this is important because when we develop things where the complexity is in the toolchain or the engine, what the developer sees at the end of it should be a simple and easy to reason about abstraction. So this is something I have here to talk about how WebAssembly fits into the Chrome's multiprocess architecture. So at the top here, I'm going to wait for it to switch back. But at the top is the browser process, and the browser process coordinates with all of the other processes. So you have the GPU process, the renderer process, the plugin process, the storage processes, the UI process, and the browser communicates with all of these processes. So for the renderer processes, so in the most simplistic way to think about render processes is that each tab gets its own process. The advantage to this type of architecture is that if one tab crashes, the other ones stay alive. This is also really important for security and sandboxing. So if you do have if you do have some sort of a security issue in a process, that it doesn't leak and affect the other processes. So one thing important to mention here is site isolation and so I talked about the simplistic way of a tab and a renderer process having a one-to-one mapping. That's not always true. What you actually want to isolate on is based on sites. So V8 and Chrome's JavaScript and WebAssembly execution will be in the renderer process. Because processes have their own memory and come with their own infrastructure, you might have multiple copies of V8 running at one time, and that kind of increases your memory bandwidth, but I think the trade-offs here are something we're comfortable with. So the reason I bring up this type of architecture is we're going to talk a lot about performance in the next few minutes, and I want everyone to understand that performance has a lot of nuance. While the execution or the runtime itself is actually a really critical component to performance, it's not the only component. The browser VM does have to talk to the GPU process or other processes, obviously through allowed APIs and interfaces, but that also adds overhead. So sometime when we kind of introduce a lot of performance improvements to WASM kernels or are only looking at WASM performance, we do have to step back and evaluate whole application performance because in a sense, that is what we care about. So from the perspective of the WASM team, we have three North Star metrics that we look at. We want to enable applications to leverage the computing power of modern hardware. And this mostly applies to linear WASM, and we've seen a lot of this come true too with Adobe, with Autodesk, Unity, a lot of large native applications being ported to the web via WASM. But we don't want to limit WASM in that way. We also want to be able to expand WASM's reach by bringing featureful managed languages to the web and critically with rich interop. The other thing that we understand too is that the success of a language or a bytecode format, as it may be, depends on the strength of its ecosystem. So we will also want to enable an ecosystem of WASM libraries, which will result in high-quality applications at scale. So a lot of what we're going to talk about is probably going to be in service to the first of these goals, which is going to be focusing on compute power. So I want to talk a little bit more about performance and specifically why it matters. So there's three reasons why performance really matters, and there's a really good blog post about this on web.dev if anyone's really interested with detailed case studies and metrics. But the reason performance really matters is retention, conversion, and user experience. So websites that load really quickly and respond to user input tend to retain more users. So as an example, BBC found that for every additional second that a user had to wait, they lost 10% of users. Slow sites have a negative impact on revenue. Fast sites are shown to increase conversion rates. So there's a direct correlation of revenue increase and conversion increase of the amount of time you spend on a website if its performance is much better. The performance is a really foundational aspect of good user experiences. We ship a lot of code. Browsers have to use megabytes of users' data to download this code, and especially when you are on low memory devices, the user experience can be quite terrible. So in service of this, a lot of what we are looking to do, I talked about how performance is very nuanced, but there are very few cases where you can get performance for free. And adding compute extensions to WASM is one of those things because it's very self-contained and you don't actually have to do anything to be able to enable it. The toolchains will support it, the libraries will support it, and the applications will get it for free. So we've had a lot, over the years, we've had a lot of requests for different types of performance extensions. I know Shravan in his previous talk talked about SIMD, and one of the things that's interesting there is SIMD is based off of SSE 4.1, and that was released, I think, in 2006, so it's several years ago. And now that when we look at native performance versus WASM performance, the benchmark that we want to be around at is maybe 60 to 80% of native, but compared to the latest of hardware, especially on newer hardware, a performance that we see is only about 25 to 50% of native, which is kind of a sad state to be in, unfortunately. So what we're looking at over time is how we can get performance of WASM up to scale. And this is not always easy, and I'll talk about that more. So a couple of things we're looking at is two different types of half precision values. We're looking at extending WASM with FP16 values, which is a compressed version of FP32. It has smaller dynamic range, but higher precision. We're also, FP16 is something where we have an end-to-end working prototype in the tools and in the runtime, and we're working on some early benchmarking. We're also kind of been looking at extending WASM with BF16 operation. And BF16 is quite efficient. It prioritizes a wider range by allocating more bits to the exponent, and it trades off precision for range. In a lot of ways, that type of precision isn't quite as important for the applications that do care about lower precision values. So in terms of some performance evaluations, compute kernels that extensively use FP16 demonstrate performance wins of 75 to 125% over what's currently in WASM. So this is, when I talk about, I also want to differentiate here between compute kernel performance and application performance. So we always want to see a direct mapping. When we see compute kernel performance improve, we also want to see application performance improve. In some interesting cases like relaxed SIMD, we always didn't see that map one-to-one because you could use sparse data and then that affects your overall performance. So in this case, though, application feature performance improvement of 60%, and it also does reduce model size by 50%. I do want to mention that speedups here are specific to ARM64. They are challenging for consistent performance across x64 just because of varying degrees of hardware support over the years, and it still translates pretty reasonably well to the latest hardware, but we're still doing some work there. We don't have prototype numbers for BF16 because we don't have a full prototype yet, but we do have really strong interest. The BF16's wider dynamic range reduces the risk of underflow and overflow that FP16 can sometimes have. BF16 is designed to be compatible with existing FMA hardware, and that has better portability. And the thing about BF16 too is that there's a lot of new research that talks about compute kernels and BF16, and especially for ML workloads, a lot of what we're looking at, we see a lot of research optimizing using BF16 over FP16. FP16 is still important for general interop, I think. We've seen that especially if you don't have FP16 support for multi-process architectures or browser VMs that do use different types of compute units, not having that supported on one compute unit means that you have to fall back to FP32, in which case the performance is pretty bad and you do incur a significant cost of conversions. So there are general advantages of lower precision values. You have, it takes less memory, less compute, and there is also more parallelism because you're able to compute more data at the same time. So we've talked about leveraging hardware, we've talked about applications. Another thing that I want to talk about is ease of use and ease of programmability. A lot of what we see a lot of the challenges that come with compute units is that we are introducing features incrementally. Now, that's really problematic in an environment like WASM where you don't have consistent feature detection. And the problem with feature detection, when I tie it back to performance, is that with the ever-expanding feature matrix like we have right now, what you have to do in the user space is send small, tiny modules and then pick based on feature set what binary you're going to ship. So not only do you have to have multiple binaries, you also incur runtime cost of figuring out which binary you want to ship. So you pay a load time cost, and you just have to ship multiple binaries, and the user experience just isn't that simple. And the reason we're in this place too is because there isn't quite as much consistent hardware support as we hope for some of these new architectures. So WASM does have like an ideological issue here of like, what would we do if we did want to support high performance extensions? Now, not everything falls into this bucket of not having consistent support, but at least the ones that applications really care about these days do fall into that bucket. So we've talked about this several times in the CG as well, and I just want to talk about a lot of the options. We've talked about, emulation detection. So you have scope per feature. You have a feature, and then per feature you can decide whether it's emulated or not. And could long-term feed into feature detection. But the problem with something like this is emulation detection isn't always easy. Where do you draw the line? There's, especially when it comes to x64, you have several layers of hardware features, and it's hard to say what is emulated and what isn't, and it could mean different things to different people. We've also gone down the route of extensive runtime optimization, especially like revectorization in the engine, because we don't have 256-bit support. What we could do is look at tight loops of 128 bits and then promote them to use 256-bit operations. That sounds nice in theory, but in practice, it's brittle just the way pattern detection everywhere is. It also runs into some interesting cases when you're looping around loads. There's edge cases where we wouldn't be spec compliant. And in general, it's also really hard for applications because they now have to feature detect when this is available and when this isn't. So you might want to ship different code if you know that you have 256-bit support versus not. So there's still a lot of things. So we have a prototype of this, but we also don't know exactly how we would get applications to use it because there's a lot of challenges around that. We could also bypass standardization altogether and have shared conventions, but this is an option I don't necessarily like because that usually means that's ballooning and fragmentation in the ecosystem. We've been talking about an incubation framework. I know a few folks in this room iterated over what it would mean to have hardware-specialized WASM or some set of incubation opcodes or built-in or import functions. While in theory this is nice, but WASM is just supposed to be an abstraction. Like you can solve any problem with an indirection, but the question is always, do you want to? And so it's interesting. It's not. There's no straightforward answer. Obviously, the easiest thing here is to do nothing and decide that we don't want performance, and WASM is just a target for different languages on the web. As a browser VM person, that's really hard for me to accept, but that it is an option. So as I said, there's no easy answers, but I do think that there's a lot of room for experimentation, and I have hope that we might find something that we land on here. Another thing that I want to talk about is the memory footprint. So the current linear memory model is very simple and portable, and it's proven to be really effective for, excuse me, for a large number of use cases. But it also imposes some really unfortunate restrictions on serious WASM applications. So you can't free memory, especially when you're interacting with the host environment, because WASM owns all of its memory, a lot of what you have to do is copy back and forth. So one of the proposals we have that are fairly early stage is memory control, which the goal of memory control is to provide fine-grained control over WASM memory. So what we want to be doing is reducing the impact of copying into memory. And especially if you have a large application, like I can think of an application that is like photos, that is processing a lot of photos and videos, you don't actually want to have large copies of large allocations sitting around and consuming memory. You also want to give applications just better control over their memory footprint. So you want to be able to allow applications to discard memory when it's not in use, and give them larger address space to use. You want to provide APIs for memory protection, and these are all things that you're able to do really seamlessly in native applications. But we do have hurdles when it comes to WASM that we're not actually able to do these things. Now, it's a little bit of a trade-off here, because every time we touch the memory layout or any of these WASM, any kind of the buffer allocation things that we do, it is a very security sensitive surface. So we want to touch as little as possible here, but while also getting as much as we can out of it. So we have some proposed API functions here. We've been iterating over this with folks over on the WASI side as well. A lot of what we want to be able to do is when we have API functions, that they are consistent across JS and WASI API. So when we do want to bubble something into the core spec, that we have a consistent way of doing it. So what you see here is what we're looking to introduce are a few different things. A memory map descriptor, which would be a JS wrapper around a file descriptor of the operating system. Which could then be passed into memory.map, which is an additional method on the WebAssembly.memory that can map the memory represented by the file descriptor. We also provide memory.unmap, which is a method to remove mapping starting at the address offset and continuing for size. Size here is represented in a number of pages. So we do have an early prototype of this. A lot of what we're hoping to do is actually gain some application data. This is, again, we don't have a very secure and safe application. What we're looking to do is get the minimal prototype out and see what is the maximum ceiling of performance we can get. By our estimates right now, we expect to reduce overhead by 20%, but a memory like the overhead of memcopy is easier to measure than a memory utilization itself, because that is very application dependent. So if you are looking at some sort of thing, or you have an application that would be interesting for us to experiment with, please reach out to me, and we're happy to help with experimentation there. So, but there's a lot of open questions around this. If we were to propose something that is exposed to the core specification, what would it look like? We could, there's the option that I presented is that we limit exposure to the core specification and have only API functions. Now, the problem with that is you still have to have some notion of a special memory, because you're going to be seeing reads and writes that don't originate from WASM memory. It's also possible that we could introduce additional conditions that allow trapping, and the core spec has to have some notion of how to be able to reason with that. And also, data segments present a tricky challenge. Active data segments can't write into memory unless it's mapped. So likely, we're going to need anonymous mappings if we want to be able to give more control over the memory. So this is something we're going to have to think more about. As I said earlier, this area is definitely one that is quite full of open questions. So ordering of memory calls on shared memory, we don't really know what we don't know. All WASI calls have undefined behavior, and this also is very OS dependent. Do we want to do anything to contain this type of undefined behavior? Especially for the non-determinism introduced, we want to figure out how we want to expose, how we want to think about how individual threads observe memory accesses. Maybe there really isn't that much to do here, but especially when you have several of these calls happening from multiple threads, should we be providing any guarantees for safety? And do these operations have to be atomic? They're not always guaranteed to be atomic by their OS primitives on Windows specifically. I think Linux makes some guarantees, or doesn't say it, but experimentation, you can tell that it is. But on Windows, this is not a guarantee that we can provide. A lot of what we've been experimenting with recently is overlapping mappings. I think that we're definitely going to be providing overlapping mappings, even though they're not consistently supported on Windows platforms. Different versions of the Windows OS have different primitives for overlapping mappings. And I think this makes it easier in a way, because a lot of what we had to reason about when it came to memory control is what should happen on an unmap. And if you have a region of memory that's fundamentally inaccessible right in the middle of memory, it raises a lot of interop challenges as well. So what we've landed on now is that this is something that is natively supported anyway for applications that are mapping into their own address space. It can be trusted to map over an existing mapping. This is supported by existing syscalls on Linux and Mac. So just generally disallowing it seems like you would introduce extra overhead because applications then have to unmap and then map again. So yeah, a lot of, especially when it comes to performance, we do have several open questions. So especially for compute extensions, what is a sustainable way for adding new numeric extensions, and how do we reason about the performance and the complexity trade-off? As I said, feature detection has kind of been really hard to nail down. We've had multiple different attempts at general feature detection, at conditional compilation, that haven't really made a lot of progress. In terms of WASM, we're a little bit loose about what we call a feature. They can be proposals, they can fit into features. We kind of, squint and see that these can form some subsets of features, but what is a feature is also hard to define and can mean different things for the tools. It can mean different things for the specification. It also means different things from the native perspective when a native application developer is actually looking to port something over. So there are challenges with emulation, and it's not clear if this is actually possible. So we just talked a lot about memory conundrums where performance trade-offs are inherently complex. We have a lot of security-sensitive surfaces when we touch the memory, and historically this has also been true. I think there was one year where Google may have paid more in bug bounties than my salary for that year, but I don't want to talk too much about that. But concurrent mmap and the atomicity of the API calls, or if we decide to port them over into the core specification, are still an unsolved research problem. And generally, when it comes to performance, memory consumption, when it comes to complex applications, has been really hard to nail down. So debugging primitives here are also going to be really helpful. So I know other folks have talked about this here, but security continues to be something that has, I think that's always a priority for us, but especially as we've shipped garbage collection and hash and started an origin trial for JSPI, we've seen a significant increase in the CVEs that we've had over the last 6 months or so, that raises an interesting question in terms of, should we be shipping this many features if what we're doing is increasing the attack surface? We get that feedback from our security team quite a bit. one of the things we're experimenting there with is validation or verification of modules at runtime. The W8 heap sandbox has shipped, which is a relief, because that means that to some extent that can be contained within W8. But that's unfortunately not the case for some of the issues that we've seen with GC and JSPI, which cause type confusion, and then you're out of the sandbox and you've compromised the process anyway. So featureful WASM and making it secure are really quite an interesting challenge. So that's kind of all I have. Thank you for listening to me, and I'm happy to take questions.
Thanks, Deepti. One thing I'm sorry I didn't highlight before the start of your talk is that in addition to all Deepti's work at Google, she was also a chair of the WebAssembly community group, which was our main standards body for a number of years. Okay, yes. With that being said, any questions about the talk? I have a bunch of questions of my own, but I don't want to monopolize your time. Okay, I guess I'll start. So yeah. I was interested that you brought up the memory mapping feature and specifically the concurrent behaviors. Have there been any internal experiments inside Google in other contexts about the kind of concurrent behavior of these things? Because I could imagine even for native apps, this might be something you'd want to push the boundaries on for performance.
Yes and no. I think for native apps, because I think the challenges are different. For native apps, they do push the boundaries, but that's mostly in some defined way because it's very specific to a platform and OS combination. It's just when you step back and you look at it at exposing a portable abstraction, that seems to be much more challenging, where the challenges are slightly different, where in the native application, you want to push the boundaries of the concurrency itself. In this case, we are trying to figure out what is the set of primitives that will allow us to do that. That said, we haven't actually gotten to the point where we're experimenting with concurrency yet. I'd probably have more to say if we were at the point where we've stressed that system more. We're at a very early prototype and we just want someone to use it. Go ahead.
So this is, I guess, sort of an outsider question. You're talking about the feature detection and emulation detection. What is it that is, I guess, what layer is not communicating about what its features are? And is it a totally impossible thing to
It is not, actually, in my opinion, it is not a totally impossible thing to happen. In the WebAssembly community group's opinion, though, that varies from my own, unfortunately. I think, so at the abstraction, so WASM is portable, right? CPUs know what features they have. We don't want to be able to expose what features CPUs have at too granular level, especially for web runtimes, because fingerprinting is a concern. We want to have some form of a privacy guarantee that we're able to provide to our users. But there are ways to work around that. There's already entropy that's exposed in the current web browsers. There's ways to not exploit that, but at least piggyback on that to some extent. For emulation features, when you have a function that is trying to use certain features, the runtime knows what hardware it's running on. So you can establish a baseline to say, if I have AVX on x64 systems, that AVX and above, I wouldn't count it as emulated, but AVX and below, I would count that as emulated. And you could also find that to be different, right? On ARM64, for example, if you had ARM v8.4, for example, which supports more features than the older ARM chipsets, you would have to draw distinctions based on hardware features and performance, and that line is just tricky to find for emulation. So hardware knows about it. VMs know what systems they're running on. WebAssembly doesn't give you the detection primitives, is the short answer.
Okay, thank you.
Recently, me and several others published a proposal for what we called hardware specialized WebAssembly, which I think saw you had that last slide where it was talking about feature detection and some other things, and specifically in the proposal, the proposal addresses some of those things. We also think it was possible to, for example, solve feature detection. And I just want to, number one, highlight that Michael McLaughlin at CMU had done some work to see like how feasible that it was for, I think it was ARM64 or something like that. Have you guys looked at it any further?
No, but I did read Michael's reply, which I think highlights some of the concerns too, where especially if you had the explosion of built-in functions, that's really hard to scale, right? And the runtime is actually implicitly taking a lot of that cost. And the runtime is also at that point in the unfortunate position of being the enforcing authority of what is and isn't a built-in. And I think in some ways there are approaches where I'm okay with circumventing the standards approach, and there are places where I'm not, because I think the standardization framework does give us some guarantee that different people can come and have their needs addressed, whereas I can see browsers really running ahead with that in terms of like what they support and what they don't. So with my standards hat on, I don't feel comfortable with that solution because I don't think it sets up the standard for success. I'm happy to talk about this offline too. I know we've talked about it a bunch.
In February.
Yes, and in February.
I have Testing. Okay, that's good. We still have a couple of minutes before the remote talk starts. So I have one more question.
Okay.
So I've often found that when Google is bringing a potential feature to the standards body, like FP16, often there'll be another part of Google, like a different feudal kingdom within Google, that also realize they would really benefit from this. And I'm kind of interested, is that generally these other teams reaching out to your group, asking, how can you make this thing faster, or are you doing more active solicitation of how can we provide more value to other groups?
So the answer to that is layered. If they have a web application, our team would care about it because we want to make a lot of their things fast. Google is a big company. They have WASM is used in a surprisingly large number of places, and I'm happy to talk to you about that after. So they come to us with a lot of requests in terms of performance, in terms of features. Just given that we're a part of the web platform team, unfortunately, we're not able to do much more than just consult and say, this is how you can do it. This is how we think it might fit, but we're not able to actively work on that, which, again, this is a case of big organizations shipping their organization. So there's, I find that unfortunate, but I think that's kind of how that happens.
Is this on?
Yes.
Good. So, yeah, you were talking about feature detection, but what about different profiles? So I know...
So profiles are a spec construct, and they don't influence feature detection in any way. They're orthogonal, don't solve a problem that implementations have. They solve a problem that the spec has. They don't solve a problem that implementations or tools have.
Right, okay. I mean... But you... I mean, I guess the idea was you detect whether a certain feature is available, and if it is, then you take advantage of it, and if you don't, then you have some sort of workaround to emulate that. But you might kind of give up instead and say, no, I don't want to do that thing.
Yeah, I mean, and I think that you want to be able to do that, but right now you do that in user space. What you want to be able to do is do it natively so that applications don't have to make these decisions at runtime and be prepared for them, and there's no way to do it natively at this time.
Thanks so much. Just to give time for our next speaker, let's thank Deepti one more time.